How does database indexing work in reality? Introduction. Database indexing is one of the most important performance concepts in backend systems. A very common interview question is, how does database indexing actually work in real systems? At a high level, indexing is a way to make data lookup much faster by avoiding full table scans. But in reality, it is much deeper than just a lookup shortcut. This topic explains what a database index is, how indexes work internally, B-tree structure, how queries use indexes, why indexes speed up reads, why they slow down writes, types of indexes, real-world storage behavior, query planner decisions, trade-offs and pitfalls, performance implications. This is a core backend plus database engineering concept. What is a database index? An index is a separate data structure that helps locate rows quickly without scanning the entire table. Think of it like check, a book index, not the full book. Check, a fast lookup map to data locations. Without index, full table scan. Example query, select star from users where email equals a@example.com. If there is no index. Row 1 means check. Row 2 means check. Row 3 means check. This is called full table scan. Time complexity. ON with index. With an index on email. Create index, IDX email on users, email. Now lookup becomes fast navigation, direct pointer access. How indexing works internally. Most databases use B-tree or B plus tree. What is a B-tree? A B-tree is a balanced tree data structure optimized for disk storage. It allows, fast searching, fast insertion, fast deletion, minimal disk reads. Visual structure, 50, 20, 30, 70, 90, Each node, check, stores sorted keys, points to child nodes or data pages. Why B-trees are used in databases? Because they, reduce disk I/O, are balanced, minimize tree height, work well with page-based storage. How index lookup works. When you run, select asterisk from users, where email equals a@example.com. With index. Step 1. Traverse B-tree. Database navigates. Root means intermediate node, means leaf node. Step 2. Find key. Locate. Email equals a@example.com. Step 3. Get pointer. Index stores. Key pointer. Row ID, primary key. Step 4. Fetch row. Database fetches actual row from table. Index structure. Real reality. Indexes do not store full rows, usually. They store key value, pointer to row, ROW ID. Clustered versus non-clustered index. Clustered index. Data is physically stored in index order. Example. MySQL InnoDB primary key index. SQL Server clustered index. Data itself is sorted. Non-clustered index. Separate structure pointing to data rows. Most secondary indexes are this type. How Query Planner uses indexes. Database has a component called Query Optimizer. It decides use index or full scan. Example. Select ST from users where age equals 25. Planner checks. Is index available? Is it selective? Is table small? Then chooses best plan. Why indexes improve performance? Because they reduce check, disk reads, row comparisons, memory scanning. Instead of scanning millions of rows, jump directly to matching rows. Time complexity comparison. No index O of n. With index O of log n. Because B-tree search is logarithmic, Y indexes can slow down writes. Every insert update must also update indexes. Example. Insert row, update table, update index, rebalance B-tree. So indexes introduce knock extra writes, knock extra disk I/O, knock extra overhead on bulk inserts. Types of indexes. 1. Single column index. Create index, IDX email on user's email. 2. Composite index. Create index, IDX name age on user's name age, used for multi-column queries. 3. Unique index. Ensures uniqueness. Create unique index, IDX email on user's email. 4. Full text index. Used for text search, articles, search engines. 5. Hash index, rare in SQL systems. Fast equality lookup. O1 lookup, theoretical, but limited usage. Composite index behavior. Index order matters. Example. Name, age, works well for check name plus age, but not age alone in many cases. Real-world example. Users table, ID, name, email, country, query. Select star from users, where email equals X, without index. Full scan of millions of rows. With index. Direct lookup in milliseconds. Index page level storage. Databases store data in pages, usually 4 KB to 16 KB blocks. Index nodes map. Keys means page locations. So database minimizes disk reads. Why indexes are not always used. Even if index exists, planner may ignore it. Reasons. Low selectivity, small table, outdated statistics, query returns large % of rows. Example. Select S from users, where gender equals M, if 50% of table matches. Full scan may be faster. Common beginner mistakes. 1. Indexing everything. X, too many indexes, slow writes. 2. Ignoring composite index order. Order matters significantly. 3. Assuming index always used. Planner may skip it. 4. Not analyzing query plans. Tools like explain, analyze are essential. Query execution flow. SQL query. Query optimizer. Choose index or scan. Index lookup if used. Fetch row data. Return result. Trade-off summary. Operation with index, without index. Select, fast, slow. Insert, slower, fast. Update, slower, fast. Delete, slower, fast. Index frequently queried columns. Use composite indexes wisely. Avoid unnecessary indexes. Analyze query plans. Monitor performance. Simple definition. A database index is a structured lookup system, usually a B-tree, that allows fast retrieval of rows without scanning the entire table. Final summary. Database indexing works by storing sorted key structures, B-trees, mapping keys to row locations, allowing logarithmic time search, reducing disk I/O significantly. Key idea. Index equals fast lookup structure for data retrieval. But trade-off. Faster reads versus slower writes.